Okay, everyone. Now let's start the chapter 3, which is about potentials. Before we start the real knowledge about potentials, first let's learn something about the tools we're going to use to calculate the potentials, which is Laplace equation. Because we're going to use this equation so many times when solving problems related to potentials. Okay, so here, the primary task of electrostatics is to find the electric field of a given point charge, which is stationary charge. Sometimes it's one charge, but most of the cases, it's a set of charges or a charge distribution. That's sometimes not even a set of point charges. Sometimes it could be a density of some charge distributions. Then by using Gauss law, by using the Coulomb's law, we have learned in the chapter 2, the electric field could be calculated in this equation. And unfortunately, this integral usually is difficult when you have a charge distributions. Sometimes or occasionally, we can get some easy solutions. When there's some symmetry happens, then we can use Gauss law. So when we introduce Gauss law, we have introduced the conditions that you can use Gauss law. The most important things are symmetries. If there are some special symmetries, then Gauss law can make it make the calculation of electric field to be very easy. Otherwise, it's not easy at all. And in most of the cases, there's no symmetry for the charge distributions. So usually it's difficult to use just this equation, the 3.1, to calculate the electric field. So ordinarily, the best strategy is to first calculate the potential, V, and then we can use the V to calculate E. Do you remember the relationships between E and V? So the derivative of V is E, but it's a negative sign before the E. So the negative derivative is of V is E. So if you can calculate V still, it's very easy to calculate E. So usually the best strategy is first calculate V or potential and then calculate electric field. The way to calculate electric potential is shown in this equation, 3.2. Still, to calculate V, it's easier than calculate E directly, but still, in most of the cases, it's still too tough to handle this equation analytically. Okay, and in some other cases, for example, in problems involving conductors, the rho here itself may not be known in advance because the rho or the charge density or the charge distributed on some materials is free to move around. So the only thing we control directly is the total charge of each conductor. That makes things even more difficult. In such cases, it's fruitful to recast the problem in different differential form using Paulson equation, which is shown here. The second derivative of of E of V equals to 1 over epsilon then times the charge density, and it's a negative, so you need to have a negative sign before this value. So we have learned this equation in chapter 2. So here, together with appropriate boundary conditions, it's equivalent to 3.2, which is here. Very often, actually, we're interested in finding the potentials in a region where rho equals to 0, means there's no charge distribution in the space. If rho equals to 0 everywhere, of course, V should be 0, and there's nothing further to say. Then there may be plenty of charge elsewhere, but we're confining our attention to places where there's no charge. For example, if we draw a picture here, let's say usually our charges could be some point charges or some charge density distributions in some materials, but you want to find the electric field lines or electric potentials in this region, let's say. So of course, those charges, they generate some potentials and electric field in this region. However, in this region, inside this area, there's no charge at all. So if you do a calculation in this region using this equation, actually the rho is 0 inside this region. Then this Poisson equation reduces to Laplace equation, which is shown here, because there's no charge inside this region. And in many cases, we're interested in such problems. So the Laplace equation becomes very important and popular when solving the problems in electrostatics. Or you can written this Laplace equation in Cartesian coordinates, which is shown here in x, y, z directions. So now this formula is so fundamental to subject that my or almost say electrostatics is a study of Laplace equation. At the same time, it's a ubiquitous equation appearing in such a diverse branch of physics because it's such kind of equation is so widely used in different areas of physics. For example, in calculations of gravities, in calculations of magnetisms, in the calculations of heat, study of soap bubbles, you all need to use this Laplace equation to do the calculations. And in mathematics, this equation is also important because it plays a major role in analytic function theory. So in a word, Laplace equation, no matter in this form or in this form, it's important to learn, and we need to be familiar with such equations, and we need to know some features of such equations. To get a feel for Laplace equation and its solutions, it's also called harmonic functions. We shall begin with 1 and 2 dimensional equations and then continue to learn the 3-dimensional cases. So in this class, we're going to introduce some features of this Laplace equation from 1-dimensional to 3-dimensional equations. Okay, let's start from the simplest cases, which is Laplace equation in just one dimension. Suppose V depends on only one variable, which is x, then Laplace equation becomes d squared V over dx squared equals to 0. And this general solution for such a one-dimensional Laplace equation is Vx equals to mx plus b. It's simply a linear or a line for an a line equation. And in this equation, it describes a straight line, but it contains two underdetermined constants, which is m and b. As it's appropriate for a second order differential equation. So in any particular case, by the boundary condition of that problems, the m and b should be fixed. For instance, it might be specified at v equal to 4 at x equals to 1 and v equals to 0 at x equal to 5. If you have those two conditions, then you can try to figure out m and b. In that case, m equals to -1 and b equals to 5. So the equation becomes negative x plus 5, which is shown in this figure. So here, we need to pay attention of two features of this result. And they may seem silly and obvious in one-dimensional cases. And we can write down the general solution explicitly, but analogs in 2 and 3 dimensions are powerful and by no means obvious. So now let's see the two features in this one-dimensional case for Laplace equation, the solution. So first, the solution of one-dimensional Laplace equation, Vx, is the average of, okay, so the solution is Vx, and then it's a straight line. Then the value of V at any point x is the average of V x plus a and Vx subtracted by a. Means if you choose any point here, which is Vx, and if you get another value, which is Vx minus a, and then Vx plus a, then the average of those two values should be this one. So on a straight line, it's easily understandable. It says that the Laplace equation is kind of averaging instruction. It tells you to assign to the point x the average value to the left and to the right of x. So the solutions to Laplace equation are as boring as they could possibly be and yet fit the endpoints properly. Okay, so it simply says any value at a position in Laplace equation equals to the average values at his left and his right positions. This is the first feature. The second feature, Laplace equation tolerates no local maximum or minimum. Okay. Because extreme values of V must occur at the endpoints. This is easily understandable, actually. And it's also a consequence of the first feature. Because if there were a local maximum, then V could be greater at that point, then on either side, then there couldn't be, for this point, there could not be the average of its two sides. This is the one explanation of no local minima or maxima. From another point of view, since Laplace equation requires on the contrary that the second derivative is zero, it's reasonable that solution should exhibit no extrema. Because do you remember what does it mean for, let's say, for the second derivative? So second derivative equals to zero simply means there's no minimum or maximum in any equations, not only Laplace equation. So based on this feature, still Laplace equation shouldn't have any local minima or maximum. Okay, so that's the one-dimensional case. From the one-dimensional case, we found two features of Laplace equation. The first one is the average feature. The second one is no local extrema feature. Now let's see the second dimensional Laplace equation. Now, if V depends on two variables, then Laplace equation becomes partial squared V equals to, over partial x squared plus partial squared V over partial y squared equals to zero. So it's no longer ordinary differential equation. Ordinary differential equation means one involving ordinary derivatives in the equation. Now, this equation is a partial differential equation. As a consequence, some of the simplest rule you may be familiar with might not be able to apply. For example, the general solution to this equation doesn't contain just two arbitrary constants or any finite number. Or actually, we cannot write down a general solution for the two-dimensional Laplace equation, at least not in a closed form like equation 3.6, which is shown here, which is a line formula. At least not in a closed form like this equation 3.6. Nevertheless, it's possible to deduce certain properties common to all solutions. Okay, now let's look at the figure 3.2, which helps you to understand what is or what might be a Laplace equation in two-dimensional cases. The gray surface on the top is the representation of a Laplace equation in two dimensions. Now let's see how is the example here. It may be helpful to have a physical example in mind. Now let's picture a thin rubber sheet or a soap film stretched over some support. Suppose you take a card box curved in a wavy line in all way around. Now let's say this is your box and you cut it in a wavy shape like this red line. So you have four edges and it's not a regular shape, it's just arbitrary wavy shape. Now you have this shape of the card box. And then you remove the top part and leave the wavy curve or the wavy card box shown like this. And then now you glue a tightly stretched rubber membrane over the box. Now you see the gray area on the top. This is your rubber membrane, so that it fits like a drum head. Now you generate a drum, but it's not a flat drum head, um, of course, unless you choose to cut the edges off straight. But it's not straight, it's wavy. So now if you lay out the coordinates x, y on the bottom of the box, the height v, x, y of the sheet above the points will satisfy Laplace equation. Okay, now this is a two-dimensional demonstration of this Laplace equation and the height of this rubber sheet on this let's say wavy edge of a card box. It should satisfy the Laplace equation. Now let's see some features. Harmonic functions in two-dimensional cases have the same properties we noted in one-dimensional cases. So first, the value of v at the point, let's say here, xy, vxy is the average of those around this point. More precisely, if you draw a circle of any radius r about point xy, the average value of v on the circle is equal to the value at the center. Now, let's say if you have a position here, xy, then you get a vxy here. And then the average value of a circle centered at xy is shown here. Then if you make an average of v xy over this circular line, you will get values shown here. And then the average of this value should be the value of vxy. Or if we write it in the equation, vxy equals to 1 over 2 pi r, a circular integral of the value v times dl. And we know that the circular integral of dl, which is shown here, is 2 pi r because it's the length of the circle. So in order to calculate the mean, we just use 1 over 2 pi r times this value. So this incidentally suggests the method of relaxation. So here, there's something more or beyond this, let's say beyond this course. This is something about solving the Laplace equations on computers. On computers, in order to solve the equations of Laplace equations, most of the method can use relaxation method to do the calculations. Okay, let's see what's that. Starting with some specified values for v at the boundary, and then reasonably guess the v on a grid of interior points. It doesn't matter if v is correct or not. It might be completely wrong values on the grid of interior points. And then the first pass reassigns to each point of the average of its nearest neighbors. The second pass repeats the process using the corrected values, and then again and again. After a few iterations, the numbers begin to settle down, and the subsequent passes produce negligible changes, and then a numerical solution to Laplace equation has been achieved. This is called iterations. So you can assign some values that might be wrong in the, let's say, if it's a two-dimensional case, you assign some values in this two-dimensional, let's say, region. It could be any values, but the problem is that you need to know the true values on the boundary, which is the four wavy edges. If you know those values, then even though the values inside the edges, they might be completely wrong, but you can, let's say, iterate or recalculate the values inside the areas by using the boundary values and other values inside the box and reassign values to um, each position inside the box or inside a two-dimensional array again and again. You can do it for the whole array or whole area, and then the value will be getting closer to the solution. And then you can do it again. It's getting even closer. So you do it again and again and again. So finally, in computer, your values in this region is getting very close to the true solution of the two-dimensional or three-dimensional Laplace equation solutions. This is the first feature, the average feature. The second feature is still the local maxima or minimum. So all extrema occurs at the boundaries. There's no local minima or maxima. So as before, this follows from the feature one, because if there is a minima or maximum, then feature one becomes false, because if you choose the point at the local maximum, then the average values surrounded should be smaller than the value of itself. Again, Laplace equation picks the most featureless function possible, consistent with the boundary conditions. There should be no hills, no valleys, just smoothest conceivable surface. For instance, if you put a ping pong ball on stretched rubber sheet of this figure, it will roll over to one side and fall off. It will never find a pocket somewhere to settle into. And because the Laplace equation allows no such dents in the surface, or in a geometric point of view, just as the straight line is the shortest distance between 2 points, so a harmonic function in two-dimensional cases minimize the surface area spanning the given boundary line. So now we can imagine if you give a boundary line like that, then the rubber sheet covered on this wavy card box actually is the minimized surface area in this case. So that's two features of the secondary Laplace equation. Now let's see the third or three-dimensional Laplace equation. In three-dimensional equations, we can not provide any explicit solution neither. And we cannot offer a suggestive physical example to guide you to your intuition. So nevertheless, the same two properties or features remain true. And the first feature is the value of V at point R is the average value of V over a spherical surface of radius r, centered at r. So this is integral of the value of potential over the surface. So we know the surface area of a sphere is 4 pi r squared. So if we use integral over 4 pi r squared, you get the mean value. So the mean value at this, let's say, centered spherical surface equals to the value of a v at the center. And as a consequence, the second feature becomes v cannot have any local maxima or minima. The extreme value of v must occur at the boundaries. So these are the same features as in one-dimensional or two-dimensional cases of Laplace equation. So here we're going to approve the features which are shown here. Let's begin by calculating the average potential over a spherical surface of radius r due to a single point charge q located outside the sphere. We may as well center the sphere at the origin and choose coordinates so that q lies on the z-axis. Okay, so this is your charge, and this is sphere. The potential at a point on the surface could be calculated in this equation, of course. And then the V average could be calculated using this simple equation because R could be described in this equation. So this, let's say, this is the way of calculating V, and by ds. So ds could be described in this way, which is described, which is derived in the spherical coordinates in the chapter 1. If you forget, ds in spherical coordinates equals to this equation. You can go back to chapter 1 to see what is ds. In this case, ds is shown here. And then by doing some integrals, you can easily calculate the average potential at this sphere is 1 over 4 pi epsilon 0 times q over z, which means this value equals to the potential here. Means if you do a average on this surface of a sphere, then you get the same value at the center. So you have proved the feature 1 for a single charge. However, due to the superposition principle, the same goes for any collection of charges outside the sphere. Their average potential over a sphere is equal to the net potential they produce at the center. So you have proved the number 1 feature. Once the number 1 feature is proved, then the second feature is, of course, true, because second feature could be derived from directly the first feature. Okay, so that's the proof for 2 features of 3-dimensional Laplace equation. Okay, so here we introduce the Laplace equation and some features of Laplace equations in 1, 2, 3-dimensional cases. Let's get familiar with Laplace equation because it's very useful in electrostatics and also electrodynamics. Okay, so that's all for today's class. I'll see you next time.